Hello, everybody, again, and welcome to the RCEA-Europe Conference on global threats to the world economy. A Chinese curse says something like, I wish you live in interesting times. And unfortunately, these are very interesting times. A key question to be addressed is whether the world economy is heading toward a new macroeconomic regime. Over the last 40 years, advanced countries have developed within the so-called Great Moderation regime. The Great Moderation was the joint outcome of improved economic policy management and favorable supply-side shocks, increasing potential growth, reducing production costs, and leading to a prolonged period of low and stable inflation. As the historical experience showed, sizable swings in asset prices occurred despite an environment with high macro-financial stability potential. The Great Moderation regime could have ended due to the persistent deterioration of global supply chains and rising energy prices caused by the pandemic crisis and Russia's war in Ukraine. These adverse supply-side developments could persist to a larger extent in the future due to the globalization, reducing international trade and technological capital and migration flows. Climate change and environmental degradation pose further threats in terms of extreme weather disruption to economic activity and harvest and the spread of new pandemic waves. Energy prices might be further subject to increases as the green transition appears to occur before the supply of renewable resources can adequately meet energy demand. A secular inflation or even a great stagflation regime might then be ahead of us. Against this scenario, the conference aims to present and discuss recent scientific results and advanced policy solutions. I would like to thank all our speakers in parallel and plenary sessions and all of the auditors, sponsors, and donors for the precious contribution to the scientific crowdfunding event. Our campaign to fund scholarship for Ukrainian students is still ongoing, and all the participants will be informed about its outcome in due time. Today's plenary session features 3 contributions to understanding climate risk and its financial implications. We are lucky to have 3 such distinguished friends and speakers, Rob Engle, David Hendry, and Gonzalo. All of us know them very well, and so I think we can move right away into the presentation. And David, I then leave you the floor.
Thank you. Indeed, Claudio, thanks for that introduction. So the talk is entitled Taking Stock of Climate Change, Earth, Air, Fire and Water, and it's jointly with Jenny Castle, building on a lot of research we've done together in the past. So the global threats to humanity and our economies begin with anthropogenic threats. There's climate change, which could lead to mass extinctions of life on Earth, as it has done in 5 previous occasions. Nuclear war could be precipitated by the resulting famines and mass migration attempts. Pandemics more deadly than the Black Death and evolving faster than we can produce new vaccines and antivirals, combined with increased antibiotic resistance triggered by environmental degradation or created by bioengineering, are creating ideal conditions for creating and spreading infectious zoonotic diseases. The destruction of the ozone layer by supposedly inert chlorofluorocarbons, CFCs, and now nitrous oxide, N2O, seriously damaged genes, both humans and plants and other animals, and replacement of CFCs by HCFCs, hydrofluorofluorocarbons, have added dreadfully to global warming, about 20,000 times worse per molecule than CO2, but fortunately fewer molecules. So there have been many attempts to avoid these global threats, but few successes. We've had a long series of completely ineffective COPs. Atmospheric CO2 levels are still accelerating. The Paris COP21 to limit global warming to 1.5 degrees C over the pre-industrial levels by nationally determined contributions have been basically ignored, and now there's no chance of keeping below 1.5 degrees, even if we start seriously reducing CO2 and other greenhouse gas emissions. Because remember, climate change will continue long after we hit net zero, greenhouse gas emissions globally as oceans and atmospheric temperatures have to equilibrate. Strategic arms limitation talks sought to have been much better, as have talks to disarm nuclear weapons, but we're not yet free of the threat of nuclear wars. Major recent advances in vaccines, mRNA, and in antibiotics, albacidin, also environmental COP agreements to reduce biodiversity loss, might be the biggest successes out of this list, because although the Montreal Protocol was a great achievement, rapidly implemented, with the ozone layer slowly recovering, and it has proved that international agreements are possible, but CFCs are still appearing in China, and as I mentioned, HCFCs also desperately need replaced to stop adding to climate change. So in summary, I see the greatest global threat is climate change. It's going to take a little longer to be a real threat to humanity, but the crucial lessons from past mass extinctions of life on Earth and information from many sciences bearing on those causes and consequences show that it's both climate change and mass extinctions that go together. So for the past 500 million years, we've had a clear warning. It's not climate level, it's climate change is the main culprit in past mass extinctions. Sudden changes disrupt the breeding patterns, the feeding patterns, and the living patterns of many, many life forms. We're just the latest trigger, and we may become a victim. We've seen compelling approaches and evidence from many disciplines. Increasing levels of atmospheric greenhouse gases are leading to worldwide temperatures slowly rising on a varying trend. Now, I'm going to use the ancient framework of earth, air, fire, and water as 4 essential ingredients for life to explore the impacts of climate change, and the same 4 the actions humanity can take to avoid disaster. These are not the Aristotelian ones. They predate actually right back to Zoroastrian theory that you have to have earth, you have to have air, you have to have fire, and you have to have water if you want to live. And cutting these dramatically will have disastrous consequences. Indeed, people often talk about adaptation to climate change. It's not meaningful if food, water, and land resources are inadequate. And on the other hand, the first mitigation steps can be beneficial to everyone if properly distributed. And jointly with Jenny, I'll propose 5 sensitive intervention points, or 6, to chart a route to near net zero greenhouse gases by 2050. Now, I realize 2050 is way too late to keep temperatures even below perhaps 2 degrees, but if we could ever get there before it gets completely out of control, that would be a major benefit. So I'll explain the 3 banner pictures here as we proceed, but this is the route map. I'll look at 500 million years of mass extinctions to lay out the role of climate change. I'll show that humanity really can change the climate very rapidly. I'll then discuss our climate in terms of earth, air, fire, and water. Look at 800,000 years of ice ages and 100,000 years into the future. This is the paper that Alvaro talked about this morning. And then I'll talk about UK's attempts to reduce its CO2 and other greenhouse gas emissions, and then discuss the 5 sensitive intervention points and conclude how we can use earth, air, fire, and water to save the planet from massive climate change. So these are the 500 million years of marine extinctions. These are Precambrian, and we don't really know exactly what's going on. But afterwards, we do know what's going on, and I'll discuss them in a moment or two. In fact, this has since been designated as a 6th. And these are the percentages of all species in the planet disappearing from the fossil record. So at this stage, for example, half of all fossils end at the end of the Permian and before the Triassic. And the Cretaceous is one that everybody knows. That's when the dinosaurs disappeared, probably from a meteoric impact. So the first one is the end of what's called the Ordovician period, roughly 440 million years ago, and it was probably due to global cooling. The second, close to the Devonian era, was due to the rapid spread of plant life on land, which actually reduced atmospheric CO2 by photosynthesis, and again led to cooling, because atmospheric CO2 stays warm. The atmosphere stays warm because of CO2. The third and worst near the Permian-Triassic boundary about 250 million years ago eliminated 80 to 90% of ocean dwellers and about 70% of plants, animals, and insects from prolonged volcanic eruptions. It's actually spread over a very long period. When the large igneous plate, now known as the Siberian Traps, erupted over several 100,000 years. And it turns out one of the major causes of this was A, there was 1,000 parts per million CO2 in the atmosphere, and B, there was a lot of mercury output by these volcanic eruptions, which proved toxic to many animal forms disappeared first and later ocean forms. And the fourth, at the end of the Triassic, opened the ecological niche for dinosaurs in Jurassic. And again, it was massive volcanism, this time underwater Central Atlantic United Province. And then the fifth, everyone knows, non-bird dinosaurs went extinct from the Chicxulub crater near the Yucatan Peninsula. We now know that it actually hit an oil field. And so it exuded enormous quantities of filth from the oil exploding from the impact. And that then blanketed the climate. And then it also led to tremendous warming shortly afterwards because of the maintaining heat in the planet. And at the same time, the Deccan Traps, which are 300,000 cubic kilometers of basalt, was exuded in India. And it's possible that was triggered by the boundary extinction from the impact crater. So all due to climate change, either cooling or heating. So can we change it? Well, we know our climate depends on the energy balance between the sun's incoming radiation and re-radiation. We're not going to affect the former very much, but we could affect the latter. We can affect the former a bit with clouds, but not that dramatically. We also affect it by mainly re-radiation and also absorption from things like changing albedo. So the atmospheric greenhouse gases that really matter, water vapor and carbon dioxide, and they're crucial in retaining heat. We can't get rid of them all, otherwise we'll freeze as an ice ages. But if it's too depleted, the planet cools. You may not know, but once there was glaciation in Death Valley from a snowball Earth. And later, with excessive greenhouse gases, very warm periods like the Eocene about 50 million years ago. And of course, all these past changes are driven by natural forces, plate tectonics, volcanism, orbital variations. And life has obviously survived all these changes, and it's thrived in very different global temperatures. But it's en route, huge numbers of species went extinct, even if long after new species have evolved and permeate into the new environment. So change is the key word, and humanity is now changing the climate by vast emissions of CO2. So this is the levels of CO2 over the past 800,000 years of ice ages, roughly varying over plus or minus 25 parts per million over each 1,000-year interval. In 1 part per million is roughly 7,800 billion kilograms of CO2, and this is now, dwarfing anything that happened over ice ages by a massive amount, the 130 parts per million in under 250 years. So we're really changing the atmosphere. And the unintended cost of the Industrial Revolution is we started burning coal, then oil, then natural gas, and all of them. And it's important to remember that annual changes in CO2 are still going up. In other words, we're getting an acceleration in the level of CO2 in the atmosphere, despite all the COPs. And this has led to accelerations in Arctic temperature and in the global temperature. The Arctic's warming much faster because of the movements of temperature between the tropics and the poles. Ocean heat content is rising very dramatically. As you can probably see, all these trend lines are way below, and at the very end, it's already going above the latest trend line, up to 700 meters down, and it's already permeated down to 2,000 meters. Which of course means that sea level's rising. So this is a forecast of sea level rise from the first third of the sample. And as you can see, it would be massively below where it is today if we'd stuck at the same level of sea level rise, so to speak. And you can also see that the sea level is rising faster again than the latest trend line in here. It's now more than 0.14 of an inch per annum versus 0.05 inch per annum between 1850 and 1992. So it's clear that it's all changing. Felix and I built a model of anthropogenic CO2 dealing with all the natural sources, and I've just summarized them. This is the vegetation source. It reduces the amount of CO2 by roughly 5 parts per million over the period. This is the Southern Oscillation Index, La Nina, El Nino, and it's increased it by about 3 over the period. So these are more or less cancelling with very little effect. And then we've cumulated anthropogenic contributions along this trend line. And as you can see, it matches the trend, and it's up by 40 parts per million over the period in our question. So it is anthropogenic. So we've established climate change is a disaster, and we're doing it, and everything's changing accordingly. So if we look at the distributional shifts in monthly global atmospheric CO2, that was it up to 1972. This is up to 1987. This is up to 2003. And this is the latest period, 2002 to 2021. And it's coming from energy generation and use, artificial fertilizer, deforestation, animal husbandry, farming, construction, and waste. They're all contributing, some more than others, but they're all needing to be dealt with if we want to get to net zero. I'll skip changes in financial dangers because my dear friend Rob Engle has appeared, and he will certainly talk about that in his talks. Skip over that for the moment. So let's look at our planet's climate in earth, air, fire, and water, which will explain these 3 headers. So Earth, that's a placeholder for our planet's land. That's both living space and soil for agriculture, forests, and wild areas. Continents and their topography are shaped by plate tectonics and volcanoes, which both affect climate and played key roles in mass extinctions. 10% of land is covered by glaciers, but shrinking rapidly. 19% is barren, deserts, dry salt flats, beaches, sand dunes, and exposed rocks, but the remainder seems to be habitable. Habitable land is obviously essential space for buildings to house 8 billion humans, their offices and factories, as well as for ground transportation, plus agriculture, forestry, and storing waste. Now, it often surprises people that the first is trivial. Satellite images reveal that less than 6% of Britain's land area is built over in any shape or form. That is airports, hospitals, housing, roads, farms, whatever, 6%. There's another 3% called green urban, but globally it's actually closer to 1% of the land area is built over. So it's not human beings building over that's taking the problem. Global food supply use takes roughly 40% of the planet's habitable land area, or roughly 50 million square kilometers. And forests have a similar share, but a falling share as time goes by. So energy production and manufacturing is coal, oil, and natural gas. Transport is mainly oil. Construction, especially cement and concrete, uses lime, which then gives off huge quantities of CO2. And agriculture worldwide presently combined to release about 4 parts per million greenhouse gases per annum. The crops are grown using artificial fertilizers, which are made from fossil fuels, and they release nitrous oxide when they flow into farmland. New farmland is created by deforestation, which is releasing CO2 and destabilizing rainfall. Animal husbandry and rice cultivation release methane on a giant scale. So all of these lead to greenhouse gas emissions, and unfortunately warming begets warming. So what are the impacts of this climate change? Well, it's causing dangerous extreme weather conditions, which even some of the skeptics are beginning to notice. High wet bulb heat, which stops people working outside. Heat domes has occurred during 2021 in North America, vastly increasing land flooding. Rivers in the sky, show a picture in a moment, can hold more water than the entire Mississippi River. And they create great damage. Recently in Europe, a third of Pakistan was completely flooded. Huge areas of China have been, and Australasia has been seeing ever increasing areas flooded, leading to lots of soil loss. Crop loss from more intense and longer droughts, increasingly powerful cyclones like Hurricane Ian, dust storms, and wildfires. Wildfires also worsen greenhouse gas emissions, as when they burn, they also emit carbon monoxide. And in the air, that nullifies hydroxyl radicals. And hydroxyl radicals are what keep down methane levels. So by annihilating those, we get more methane. And this has been happening from Australia, Amazon, California to Siberia. And one worries about the potential tipping point from tundra melting, releasing vast volumes of methane, as we'll see in a moment. Sea level rise is partly baked in. It will cause coastal flooding and much worse storm surges. If you take a bath and you fill it a bit higher and then you put waves in it, you spill an awful lot more water than when it's lower. So the sea level rise causes much bigger storm surges. And there are more than 600 million people currently living in low elevation coastal zones at risk of displacement from the levels already baked in. So here's our rivers in the sky, huge drops of rain coming out, our dust storms, our wildfires, and our storm surges. So air. Well, our atmosphere is this thin blue line around the planet, no thicker than a sheet of paper around a soccer ball. There's almost no atmosphere. Can we change the atmosphere? You bet we can, with the greatest of ease. People used to deny, oh, the Earth's far too big, can't affect things. Well, we can. Now, the atmosphere is roughly 78% nitrogen, 21% oxygen, and then greenhouse gases like water vapor, which is crucial to life on Earth, carbon dioxide, which as we now know is about 440 parts per million, nitrous oxide, which is a dangerous gas because it's about 300 times worse than per unit per molecules in carbon dioxide. Methane is about 20 to 30 times worse. And then we've got all these CFCs destroying the ozone layer. We've got ozone, which itself at low levels is a pollutant, and we've got all the noble gases, argon, neon, etc. Now, Earth's gravity and magnetic field are essential to retain this atmosphere against the solar wind and protect the ozone layer from damaging radiation. The magnetic field has been changing quite a lot recently. In the past, there's been periods when it didn't operate. Now, if humanity is unlucky and it doesn't operate during a period that we've got very large quantities of greenhouse gas in the atmosphere changing the temperature, we'll get a low ozone layer, we'll get enormously damaging radiation coming from it. And that's clearly happened in the past. So atmospheric gases have changed greatly over deep time, as I mentioned, from volcanism and the exchange of CO2 for oxygen from photosynthesis. An atmospheric blanket is essential to life. We've got to have it. They radiate energy at different wavelengths. But the crucial thing about a lot of the current ones is they re-radiate long wave radiation. And that's what's responsible for the atmospheric greenhouse effect. It comes in it. Short waves and goes out at long waves and bounces back. Now, what's surprising about humanity is how slow it is to pick things up. In 1856, Eunice Foote showed that a flask of CO2 heated greatly in the sun, whereas those of even water vapor and dry air did not. And that was confirmed experimentally 3 years later by John Tyndall, who's often attributed with inventing the concept of climate change from greenhouse gases. But in fact, because she was a woman, of course, they just ignored what she did. More recently, people have realized just what a contribution she made. And slightly later, Svante Arrhenius proved that atmospheric temperature change was proportional to the change in the log of CO2. And the big models use the level of CO2 because, in fact, if you plot the log of CO2 and you plot the level of CO2 in the period since the Industrial Revolution, they virtually lie on top of each other with an appropriate change of scale and slope. So it doesn't really matter which you're using. Now, Venus, which is now freezing, and Mars, which is now Venus, which is now boiling, and Mars, which is now freezing, suggest atmospheric protection has to be just right. Our range is huge in Earth, from a snowball to highly tropical conditions during the Carboniferous. Now, the next one that's increasing rapidly is nitrous oxide emissions. These come partly from catalytic converters. If you run your car when it's cold, you pump out nitrous oxide. And from nitrogen and phosphate fertilizers. And CO2 emissions have doubled in the last 50 years. So now about 7% of greenhouse gas emissions, but at 300 times more potent. Multiply 7 by 300 times, you realize nitrous oxide might now be one of the most significant greenhouse gases that we're pumping out, and we have to deal with it. And that requires dealing with artificial fertilizers for the most part. Methane levels have doubled over the past 800,000 years, a bit slower, and they're about 20 times as powerful, with a half-life of about 15 years before getting to converted to CO2. But the current estimates of methane anhydrates are over 6 trillion tons. That's roughly twice the CO2 in all known existing fossil fuels. So go to Siberia, dig a hole in the ice in wintertime to fish, set light to it, but jump back rapidly because you'll see it, methane catches fire and explodes in front of you. And this is happening more and more. The tundra is melting and it is emitting lots more methane. Possible collapse in rainforest ecology from resulting changes in rainfall patterns. So fire, coal is the worst polluter, CO2, 100 kilograms per 300 kilowatt hours. Gasoline's about 70, natural gas about 50. What about water? This is all the water on the planet, folks. Everything, ice, oceans, lakes, rivers, everything. That's all we've got. Tiny little ball. Can we boil it? Can we pollute it? Can we fill it with plastic? Can we turn it to weak carbonic acid? You bet we can. That's all the fresh water. And you can see it. That tiny drop there is all the drinking water on the planet. Water is just a puddle. It may look like a blue planet, but it actually, all the oceans are so shallow, there's very little water. So we can certainly change that. Rising temperatures are melting glaciers that maintain major river systems and potentially dangerous losses of food production in Asia. The oceans hold about 60 times more CO2 in the atmosphere. As they warm, they give it off, and reduced albedo from ice loss, warming lakes emit even more methane as temperature enhancing feedbacks. The sea level will rise roughly 44 to 85 between now and 2100, depending on what representative concentration pathway. And if West Antarctica floating shelves retreat, the interior is vulnerable. If all ice melted, the sea level would rise about 4.8 meters from West Antarctica, 7.3 from Greenland, and 58 from East Antarctica. Now, the Earth has been ice-free in the past, so don't think this 70-meter rise is something that's science fiction. And just imagine what would happen to the landmass if the sea level rose by another 70 meters. Alvaro talked about this a bit this morning. I'll just move through it straight into the key thing. If you forecast well into the future with no human impact, we are entering an ice age. That was known 10,000 years ago, that we intervened in the climate already with cutting down forests and growing rice, and Rudiman and Schneur have both pointed this out. And we'd see 3 ice ages over the next 110 years. But already we're way outside these levels. And if we look at what would happen at 440 parts per million continued into the future, or even worse, 560, we'd get almost no ice from 560, and we'd get boiling temperatures from way above the peak ice age temperature. Anyone doing anything about this? Well, the UK is. Its Climate Change Act, a unanimous vote in Parliament to restrict the use of coal and oil and try and replace them with renewables, has led to a very fast reduction in CO2 emissions per capita, greenhouse gas emissions per capita. CO2, it's already down to about 4.5 tons per person per year, yet real incomes have risen 7-fold. Very little increase in fuel use since the mid-1970s in Britain. The ratio of CO2 to capital stock is up 92%, but unfortunately the US, it's come down a little bit, but it's still emitting more CO2 per capita per annum than the UK ever did, even at its peak usage. So what can be done? Well, a sensitive intervention point is when the system's near a critical or tipping point, so a small change triggers a much larger change that becomes essentially irreversible. Tipping points are the nasty ones, SIPs are the positive ones. And they can lever policy actions like the Climate Change Act and technological developments like solar and wind getting cheaper than fossil fuels. The 5 SIPs to reduce greenhouse gas emissions are: first, expand green electricity. We can use earth generating electricity from thermal, like Iceland does, from bio, that's getting increasingly common, from wind by turbines, from fire, from solar and nuclear and fusion, is coming along very well. Water, hydro, tides and waves are all being used. And we need to increase it about 15-fold in Britain to replace all other sources of energy. We only need 15-fold, although it looked like 25-fold in paper, because electricity is vastly more efficient than coal or oil. Electric power vehicles connected to a smart grid. We provide short-term backup to balance variable renewable supply. We do have periods with no wind and no sun in Britain. It won't surprise you, and in many other countries too. We can get low-cost hydrogen from intermittent surplus renewables, and we can turn some of it liquid, both as a medium-term storage and a high heat source. And then electricity-based agriculture can grind basalt to replace current fertilizers. You develop underground and vertical farms and use plasma waves to turn ammonia pollution into fertilizers. The key difficulty lies in agriculture. We need a much lower footprint. And this can be done by changing the diets of animals, fumaric acid and asparagopsis, and also by changing the animals. Deer give off about 1/5 the amount of methane per unit weight that cattle do. And sheep are about half cattle. So dietary changes and eating less meat would be quite beneficial. Replace artificial fertilizer with biochar. That's what turned the Amazon black in ancient times. And basalt dust, which also absorbs CO2. That's how we got from 1,000 parts per million in the Permian Triassic down to 250 a couple of million years later. We just have to do it rather faster than that if we want to survive. We need to cut new cropland and the environmental damage that results and use better crop production efficiency. Funnily enough, if you grow wheat in a vertical farm, you can get roughly 300-fold more wheat per unit than you get from growing it outside, and we can improve agriculture. So, conclusions. We cannot continue to consume with our carbon budget and get to net zero by 2050. You really have to do something about it. We need to vastly expand non-greenhouse gas electricity, no coal, so much less CO2. Decarbonize ground transport, no oil, so much less CO2, and we can store electricity in V2G and in other ways. Decarbonize households and construction, so we don't use natural gas and we don't give off CO2 from concrete. There's many ways. Jenny and I have a paper discussing in great detail how you do all of these. Decarbonize industry, electric arc, and using high heat sources like liquid hydrogen. So everyone's using less of fossil fuels. And then we need to reduce agriculture's greenhouse gas footprint, less CO2, less N2O, less CH4. So there's hope for the future from the very renewable energy sources that we've discussed as being a problem at the moment: earth, thermal and bio, air being wind, fire, solar, nuclear, and water. Thank you very much for listening. And there's a graphic pic of our sensitive intervention points.
Now, yeah. Well, thank you, Claudio, for the invitation, and thank you for organizing this conference with such a nice goal. I have to say that it's an honor to share this session with two of the colleagues I most admire, and I learned since I was in the kindergarten of the PhD in San Diego from both of them. So I apologize if now the quality of the session gets a little bit lower. I'm sure Rob will push it up. So I will try to do my best. This is a joint research with my colleague Lola Gadea from University of Zaragoza. And basically, today we are going to focus on a quantitative method to show you which areas in the planet are suffering a stronger warming process. I will try to be positive in some sense. I mean, the results are not very positive. I will try to give you the positive size. It's important to study the quantitative aspect of climate in order to get to design mitigation policy, of adaptation policy, and even compensation policy. So the first slide, please relax. I'm going to tell you, I mean, to warm up a little bit about climate. The first slide is cut and paste from the World Economic Forum this year in Davos. I tend to watch every January what people discuss there. These are very important people. And this is a survey about what are the main global risk issues. Think on 10 years, that is what we consider long run. And on the top 5, 4 are climate related. So from this slide, what you have to get is that climate is a long-term issue, a very important long-term issue. There are other issues like inflation, maybe unemployment. They are not long-term issues. Climate is a long-term issue. But it's important that recently, and particularly this year, this is from the published in January, the short-term global risk issues, the top 5, 2 are also climate issues. So climate is becoming also important for, well, let's see, these people that they take decisions in different countries. This is a survey done in 150, 160 countries. So it's also a short-term issue, climate. 10, 15 years ago, maybe you don't remember, but this publication has been around for 20 years, I think. Climate was under the umbrella of environmental. So everything was environmental things. What was more kind of a smooth thing, no? But now everybody, and this is not a left-wing group. I mean, as you can imagine. So that was the people they meet there are, well, let's say normal rich people, no? So this is the first slide. The second I want you to pay attention is that, as David was saying, climate is accelerating, the climate change, but also in today's talk, I want you to pay attention to the non-uniformity. This is a well-known fact. In fact, some of the results I'm going to present, some are not known, some will be known. What is new is the methodology to analyze these quantitative issues related to climate. And you see in this heat map, when you don't see red, things are okay. And every row is a decade. So it started in 1850. Then when you go around 1950, you start seeing red areas, and then becomes more red, more red, more red until now. So you see there is a clear acceleration, and also you see that it's not uniform. And in today's talk, what I'm going to show you is a method to measure this non-uniformity, because it's really important in order to take different decisions. If we have time at the end of the talk, I will show you a video. This heat map can be represented in a video, but I may not have time. It is clear, I mean, that this non-uniformity cannot be captured by analyzing only the average. No, the average is okay. I will show you cases where the average is enough, but the average temperature is not, most of the cases, is not an enough statistic to analyze this non-uniformity. So what I want to propose is a way of analyzing the whole temperature distribution, and you're going to get from this temperature distribution any characteristic that you want. Kurtosis, skewness, quantiles, whatever, no? From that, of course, we have not been the first one to propose that we have to go beyond the mean. People that analyze income distribution, like the co-authors of Piketty, Thomas Blanchett, Manuel Sanz, and Gabriel Zuckman from Berkeley, they already get these animals they call quantiles in the income distribution and form time series from there. So we are more or less replicating that type of analysis. Some preliminaries after these 3 slides is that although climate change and warming is not exactly the same, in this talk, climate change and warming will be equivalent. The definition of warming will be very clear, but in a minute. But right now, warming is an increasing trend in any of the characteristics of the temperature distribution, not only the mean. You could have maybe the mean doesn't have any trend, but it could have that quantile may have a trend. then you will have a warming in that quantile. And don't forget that in order to analyze climate, you have these 4 different issues. You have to analyze the system, the causes, the effect, and also the different mitigation, adaptation, and compensation policies. And you cannot, the analysis will be incomplete if you study one of them without having analyzed the previous one. So from this slide, what I want you to realize is that in order to study climate, we have to go beyond the mean. No, this is the purpose of today's talk. So why the research that I'm going to present could be important? Well, we think that could be important because first, because it's important to analyze in a quantitative way the climate. This quantitative analysis can be taken later on to the climate models. Climate models should replicate what we find out. No? So it's a way to interact with these 2 type of analysis that right now are a little bit separated. No? If we are able to produce observational, robust quantitative results, climate models should replicate them. And a way of checking the performance of climate models will be to see if they can replicate these results. So we're going to propose definition of warming acceleration, definition of warming amplification, and in a way that can be easily tested. We will propose a warming typology, and today's talk, it will be focused on a measure of this climate heterogeneity that will be called warming dominance. Just in case you get lost, 3 recommendations. Warming dominance equivalent to stochastic dominance. And going a little bit beyond, if you get lost, think yourself as a quantile in the income distribution of the attendance of this conference, or if you want, on a weather station. And you are going to provide me data every year, and I'm going to form this temperature distribution and to estimate these characteristics. The fact that we can prove that the climate is not uniform, this opens the door to a new non-uniform causal effect analysis, no? That some people already started. But for us, it's more important that this non-uniformity is going to imply that the mitigation and adaptation policies should not be uniform. And in the theoretical literature, I mentioned these 3 papers by Antoine, Dotim, Brock, and Penn. Basically, the theory says the carbon price should be unique, but it should be unique under certain conditions. And one of the conditions in the first paper is that you have to allow, or it has to be possible that government make some lump sum transfer. This is impossible. So if you have some equity concerns, the carbon price should be different. And what we're going to suggest is that regions that warming dominates other regions should have a higher carbon price. The paper by Brock, what it says is that if you consider 2 regions, like the Arctic and the rest of the globe, the regulators that don't look at the Arctic, at the amplification that is happening in the Arctic, will propose a tax on carbon that will be biased. And most of the time will be downward biased. So if you consider that there are regions that warms in different speed, for instance, then the tax should be higher than if you consider a uniform tax without thinking that the planet is different. And the paper I pen is very nice. It's focused on the US, and it says in the literature, what the people claim is that this non-uniform carbon price is very expensive to implement. So what Penn shows is that this is not the case. It's not more expensive. Penn focused on the US, divided the states in highly sensitive to climate issues, like California, medium density, and low very low sensitive to climate issues. And what she proposed, or they propose, is to have a higher carbon price on those states that are highly climate sensitive. At the end, you get the same target, but this is it makes the policy more efficient, and the cost is very similar. No. Also, what the results we are going to propose, we think it will have some implications in compensation policy. Although, if I tell you that Europe is going to warming dominate Africa, of course, in this compensation policy, temperature is not the only factor. Income is going to be the factor, and we don't study that. And then there is an important news in the psychological effect. There are papers that they show that when you suffer climate change, you are more sensitive to climate change. And then our results, well, are going to show that if Europe, for instance, dominates the whole planet, then this is a positive result, because then Europe or the North America or Asia, these three continents are going to be more sensitive to climate change issues, and very likely they will speed up their intervention or the implementation of different policies. Of course, this issue is not relevant because we say that, because we say so. In most of the reports by the IPCC, for instance, the latest one, they already talk about regional climate. They spend a lot of pages on that issue. Today, I'm only going to talk about different regions in the globe. We have also analyzed US by states, and we are working now in Europe. The methodology is based on 3 papers that we have, one in the Journal of Econometrics, the other in CIS, and a working paper where we show how easily can be to analyze in a quantitative manner this non-uniformity of climate. So what are the results? The results are all the regions, all the planets are suffering a warming process, but the Antarctica. About Antarctica, we will talk later on, because as David was mentioning, there are 2 parts in the Antarctica that they behave very differently, the west and the east, and that is, I have to say that the data that we have, because we impose certain restrictions, the data comes from the east. So that's why we don't have Antarctica. That is not suffering right until now a warming process. The warming process of these regions in the planet, of these continents, are very different. So Europe, South America, and Australia, when you look at the distribution, the lower quantile and the upper, they increase, but at the same speed. When you look at the Arctic, North America, and Asia, the lower is increasing more than the upper. Africa, the upper is increasing more. And the Antarctica, as I said, is not suffering a warming process. But this is a description. This is a warming typology, like other warming typologies that are in the literature. What is important is how do you measure this non-uniformity? And with the concept I will define in a second, the warming dominance, what we prove, what we show is that the Arctic, the North Pole is dominating the rest of the planet, except Europe in the upper part of the distribution. Europe dominates all the regions, including Africa, in all the quantiles, but Asia, in Asia, Europe dominates in the upper part of the distribution, and Asia dominates in the lower part. North America, Asia, and Africa dominate South America, Australia, and Antarctica. South America does not exercise any warming dominance. South America is in good shape, not even dominate Antarctica. And finally, the globe, that will be the benchmark, dominates South America, Australia, and Antarctica. So in a way, what we are saying with this analysis is good to think globally, but it's more efficient sometimes to act locally. So the methodology, I'm not going to bore you with much details. Basically, have a look at the data, and with that, I think it's enough. For every year, remember that you are a quantile in the income, and also you are a weather station. I'm going to ask you for every year, you have measured the temperature every day, you average monthly, and then annually. I'm going to ask you for these observations and at the annual level, and I'm going to have I'm going to be able to estimate the density of every year of the temperature of the temperature data. No, and when sometimes there will not be, there are continents that they don't have enough data. And then what people in the functional analysis they do when they handle these issues is they put in the basket not only the annual but the monthly observations of every station. So for all the continents, what I want to have is in every year, for every station, you are going to give me 12 observations. I'm going to put in that basket. So I'm going to be sure that I have enough data points. Basically, I require to have at least 300 to estimate this density. And the theoretical properties, I'm assuming that the process, of course, globally is non-stationary, locally is stationary, enough to estimate the density. So once you have estimated the density, this is for the whole globe, then you can produce, if you are an average person, so you can produce the mean of every year, and you have the time series of the mean. You can do the same thing with the max, with the minimum, with the standard deviation, with the range, kurtosis, skewness, and all the quantiles. So all these are time series animals. And in a sense, what I'm going to show you is that you can really do magic with time series. So you can do a lot of things with this time series. So this is for the whole globe, but I will show you the same thing from Africa, Asia, and every other continent. So now you have to pay a little bit of attention, and then in a very short while you can relax. So what is warming in order for testing and deciding that all the continents are suffering a warming process? So warming is the system of a trend, of an increasing trend in some of the characteristics. And the issue here is what is a trend. I'm not going to go into the details. So whatever intuition you have about a trend, this is valid. This is okay. So very likely you will think that the trend is a monotonic, sometimes does not increase, but on the overall increases. Well, this is okay. No, you could think that maybe it's a quadratic trend, maybe it's a unit root process, maybe it's a fractional. Well, all these processes are captured with this simple regression. So you take the average, you take the quantile 5, you regress on a deterministic trend, and if beta, this coefficient, is different from 0, if you can reject it, then you have a trend. You may not know which type of trend, but for this presentation, it's enough that you have a trend. You have a trend means that region is warming. That is enough. And this can be seen as a first order approximation to any type of trend. So this is a very nice result. I told you at the beginning I'm trying to be a little bit positive in this presentation. So this is a nice result. Now you can do this for all the quantiles, and you can check if the quantiles, they have the same trend. If they have the same trend, they represent certain typology. We call this W1. If the lower goes upper faster than the upper quantile, then this we call warming 2. And if the upper goes faster, like in Africa, than the lower quantile, is W3. This is a kind of a description that is useful. No, this is similar. Get two quantiles. You get the quantiles of 5 and minus the quantile 95. You take the difference. If you regress on a trend and beta is 0, then if you remember the paper by Rob and Sharon, this will be a common feature. They are sharing this common trend, deterministic common trend, and then they will evolve in the same with the same speed. No, that is very, very simple, and that is the typology that was mentioned before. That knowing the quantiles of every region, you can determine if one region is if a region like Antarctica doesn't suffer warming, or like Europe and Australia is having the same speed in the quantiles, or like North America and the Arctic, that they are the lower is going faster than the upper, or like Africa, that the upper is going faster. But this is only an ordinal characterization. So we want to measure that, and this is the special topic of this talk. So now you have to pay attention to the next slide. Before you have been relaxed, now you have to pay attention, not to this one, not to the one, this one. So region A and region B, you're going to get the quantile or the mean, whatever characteristic you want, of region A and region B. You are going to subtract, and you are going, this is a new time series. I will show you a graph in a second. This is a new time series. If you regress this on a trend, and the trend is significant, the first region dominates the second. If it's positive, of course. If it's negative, the one below dominates that. So if this is done for all the quantiles, it's a strong dominance. If it's done for none of the quantiles but one, for instance, then it's called weak dominance. If you have that one region dominates in the upper part and the other regions dominates in the lower part, you have partial dominance. But with this concept, with this method, you can measure the intensity. You can measure which region is warming faster than others, and then which region should have to take actions maybe stronger than other regions. This is what I just said. You have strong and weak, and partial or no dominance at all. And it's important to realize that sometimes the mean is enough, but many of the times with the mean you don't get this description. So let's have a look at, for instance, Europe and Asia. Let's take the mean. So this graph is, this time series is the mean of Europe minus the mean of Asia. And you see that the trend is not different from 0. So at the mean level, Europe and Asia, they warm equally. But then if you look at the upper quantile, if you look at the quantile 80 of the distribution 90 and 95, so the higher temperatures, Europe dominates Asia. But if you look at the lower quantiles, like the 20, 30, and 40, Asia dominates Europe. And that with the mean cannot be captured. So that, and it's, again, it's a very simple, this is pure time series analysis once you get this distribution. So now let's go to the data. I'm going to pay attention only to the planet. No, although as I said, we have done this research for the US, and we are now working on Europe. So these are the regions. I mean, there are natural regions. There are the continents, the globe, the Arctic and the Antarctic. You may think that maybe they are not continents, but they are interested by themselves. The period is 1960 to 2021, because we require that the stations that we are using are the stations that are providing data every month of all these years. So in some sense, I'm using only the audience that is going to be in this talk for the whole duration of the talk. If someone leaves the talk, will not be, and it's a weather station, will not be in this data set. It's a kind of a requirement that we make to have well, some coherent data, no? But so we don't want to put observations of stations that sometimes exist, sometimes they don't exist, or they don't provide the data. Don't pay attention to these numbers. I will tell you. I will drive you with the mouse. So these are the trend regressions of the mean of the globe, the North Pole, Europe, North America, South America, and so on. This is the beta. The values underneath, in parentheses, the p-values. So you see the globe, a clear trend. As David was saying, these possible numbers here, it means in 100 years, 3 degrees. The North Pole, more than 5 degrees. Europe, 3 degrees, 0.2. North America, 2.7. South America is in good shape, 0.006. Asia, like Europe. Africa, 0.024. Australia, lower than Europe and than Africa. And the Antarctica is not significant. Antarctica is not getting any warming because it's the East Antarctica. The quantile 5, what you have to see is that most of the quantile 5, so the lower temperatures, are increasing much more than the mean. Much more than the mean. And if you look at the upper quantiles, some of them are like the mean, or around the mean, sometimes are upper. You look at, for instance, Europe, the quantile 5 and the quantile 95 evolve same speed, same slope. But if you look at the globe, no, the quantile 5, 4.5 degrees, 2.5 in 100 years, the upper. So the lower is increasing more. The Antarctica, there is not an increase. Africa, the upper quantile, 3 degrees is in 100 years, and the lower only 1.4. So only with this time series regression, trend regressions, you get a lot of information. But this, you are not comparing. Here you are not comparing. So this it's helping to determine what type of warming typology you have. If you want to know about the numbers, you have to, as David was presenting, you have to go into paleoclimate, because sometimes people say, okay, fine, 3 degrees. What does it mean, 3 degrees? Well, we have been already in situation where there was an increase in 3 degrees, 4 degrees. So I'm not going to read you this slide, but there are books and there are many papers where they tell you what happened when we already have an increase of 4 or 5 degrees. Only to be funny, I mean, in 5 degrees, there were alligators in the North Pole. No, so I mean, to give you an idea. And also remember the ice ages, between ice ages and glaciation periods, the difference in the temperature are not so big. People may think that they are 10 or 20 degrees. No, are 3, 4, 5 degrees. So this is a lot in order to interpret the results that we got. Here, don't pay attention to that. Don't pay attention to that. Don't pay attention to that, because there are a lot of numbers. Start paying attention to this. So these are now the plots. Europe and the globe. Remember, I'm taking, when I talk about the mean, is the mean of Europe minus the mean of the globe. This is a new time series. If the slope is positive, the mean of Europe dominates the mean of the globe. If the trend is 0, then there is no dominance, and if it's negative, the globe is dominated. Here, in the mean, Europe is dominating the globe, but nothing happened in the lower quantiles. And in the upper, Europe is in bad shape. Maybe because of Spain and Italy, but that we haven't studied this in such a detail. So I'm only going to talk about the results that I obtained. So Europe is not in such a good shape. And this, some people may think is a bad news. I think this is a good news, because Europe, in some sense, is in the frontier of taking decisions. And now Europe should take decisions much faster because it's not in good shape. So Europe is suffering warming faster than the globe as a macro benchmark. Let's compare Europe with other regions. Europe with Africa. Europe is taking into account the warming process, not in which state you are. We know that the temperature in Africa is higher than in Europe. No, the warming process of Europe is much faster than the warming process in Africa. So Europe is not in good shape either. If you compare with North America, in the lower quantiles, more or less okay. In the upper quantiles, again, Europe dominates North America. Africa and the globe. Well, Africa and the globe dominates Africa, because remember, the slope is negative in the mean and in the lower quantiles, but Africa dominates the globe in the upper quantiles. So Africa in the upper quantiles is not in good shape either. When I was mentioning that Europe dominates Africa, and I wanted to be positive, the way to be positive is that imagine that the opposite result. Imagine that Africa dominates Europe with the higher temperatures in Africa. Then Africa will extinct very, very soon. So that's the way I was saying at the beginning. I try to be positive. It's better than Europe dominates Africa, because also Europe is a richer continent. Between South America and Africa, Africa dominates South America. Africa dominates South America in every characteristic. The Arctic and the Antarctica, this is a well-known result. The Arctic dominates the Antarctica. This is a well-known result, but it's good to have this in a quantitative manner. So what do we have learned? We have learned that there is a clear warming process, except the Antarctica. South America is not in bad shape, but the other continents are suffering a lot. That we are able to characterize the warming process because it's different by this typology that I mentioned to you. But I want today to pay attention to the warming dominance. So in the warming dominance, Europe is dominating all the regions, including Africa, but Asia dominates Asia in the upper quantile, but not in the lower. North America, Asia, and Africa and Australia dominate North America, Asia, and Africa dominates South America, Australia, and Antarctica. Australia dominates South America and Antarctica. South America doesn't dominate anyone. The globe dominates South America and Australia. And maybe you don't remember how is the map of the CO2 emissions, but I'm sure what I'm going to tell you it matches with your intuition. These three regions, Europe, North America, and Asia, they are the ones that dominate the rest. These three regions are the ones that they emit more CO2. So the results, they have, well, there's a narrative behind those results related to with greenhouses. So as conclusion, we are offering a low cost. I mean, as again, you can even run this in Excel or in eViews, low cost quantitative methodology that shows that there is clear local and global warming, that they evolve in a different way, that is important to measure this different way in order to take decisions for mitigation, adaptation, and compensation policies. And I want to make this point because sometimes there is this discussion between what we are called observationalist analysts or people versus theories that they use this climate model. And because I have seen this discussion already in macro between time series econometricians and dynamic general stochastic equilibrium models, I don't want to create any conflict between these two approaches. What I'm saying is that once you get robust quantitative results, and every result related to a trend is a robust result, the climate models should replicate these results. So if they don't replicate the results, the climate models, they have a problem. No, so that's and to finish, well, in every region in the globe, there is always a polar bear that is saying, please pay attention to the whole distribution of the temperature, not only to the mean. And in the meanwhile, think well that there will be more results coming, and think that climate change problems are not solved with a band-aid. As Greta says, there is a lot of blah blah blah, but joining with David talk, we have to be positive, and knowing is a way of being positive and being able to solve the result. So I finish here. I think I was on time. So thank you.
Okay, thank you. Okay, is that visible? So thank you for inviting me. I'm going to talk more about the finance side of this than the physical side, but it's really great to hear both David and Jesus doing nice econometrics on the physical risks that we're facing. I actually have a lot of things to talk about, and I've included portfolios, greenwashing, stress testing, and long-run risks. So I think I better get to it. And you've heard a lot about the science today. The economics is a little less worked out, but it's basically, we're trying to deal with things like how climate change will lead to lower productivity, population migration, stranded assets, maybe of fossil fuel companies, but also, I think importantly, other kinds of land and capital, global conflicts, reductions in the quality of life, and of course, ultimately, possibly the end of our species. But because of these are so far in the future, we wonder whether we can make these kinds of decisions, but we're seeing signs of all these kinds of events in asset prices today. These are forecasts of long-term cash flows and productivity. And these asset movements are what are going to guide capital and investment flows in the future. And so it's important to understand how asset prices are changing and what they are telling us about the future that's coming to us. And for example, if you look at the prices of Tesla stock, it's many times earnings, whereas GM is less than 7. So forecasts obviously matter in this kind of context. So I want to put this in the context of long-run risks, because a risk is something bad that could happen in the future. And if it's far in the future, then I'm going to call it a long-run risk. And you might say that the long-run risk is about the science of climate change, but it's also about how our economy responds, how we adapt, how we mitigate climate change. And that is certainly uncertain today and influences what we think asset prices are going to look like. So I want to give you an example which is easy to understand, but I think illustrates one of the things that I think is going on around us. And that is, suppose you own a beachfront luxury hotel. And there are a lot of risks to this hotel, but one of them is sea level rise. So in the long run, you've got to figure that this hotel is not going to be able to survive. This is a physical risk, and this hotel is going to become a stranded asset. So what do you as an owner do now? Well, you might try to sell it, but you're going to find that the buyer knows this event is going to happen as well. And so the main thing that you might do is decide not to remodel the hotel to raise its quality and so forth, if the payback period of that is long relative to what you think the survival time is. So the basic idea is that you would reduce your investment in this hotel. And of course, other hotels in the same area are going to do the same thing. So the supply of luxury beachfront hotels will probably decrease. And if the demand doesn't change, then that says the prices are going to go up. So you'll see prices going up because this is a stranded asset. However, of course, this is just temporary, and it's known to be temporary. And so the question is, what do investors do about an asset like this? Well, in the short run, they might receive big payoffs from the rise in profits because you've reduced costs, and the hotel rental rate is likely to go up. But of course, in the long run, the investors will receive no more profits. So, well, you might think about a market timing strategy to buy stock now and sell it before it collapses, but who are you going to sell it? So that's a market timing strategy. It's not likely to be effective. So basically, investors have to expect high payoffs now, and they will value the price in the same way as before. The present discounted value of future payoffs would be future cash flows might be exactly the way you would price the stock. It's just that, you know, you expect your dividends to be arriving now, and then the stock price goes to zero and you don't worry about it. So this example looks a lot like the fossil energy sector, and we're going to come back to that later, where optimal behavior for energy owners might really look sort of like what this hotel chain would do. Okay, so we talked briefly about physical risk. The other risk is that we commonly discuss is transition risk. And this comes from efforts to mitigate climate change, because most mitigation strategies involve decarbonizing the global economy. And this creates winners and losers from these policies. And transition risk is the risk that you're going to be one of the losers. It also suggests that the efforts to hedge whether this happens or not might be based on identifying who the winners and losers really are. So in general, you would expect the losers to be the high greenhouse gas emissions firms, but in fact, there might be either exceptions to that, and that they might be able to shift their tax either upstream or downstream, or that other low emitters might in fact be more hurt by transition risk than you would expect given their emissions. And so lots of careful research is being done to try to figure out these exceptions as well as the general rules. A lot of this is being done in Wall Street, and we're going to try to look at how effective it is. So what's the asset pricing theory for this? The asset pricing theory is that the stocks that are facing long-run risk, or actually any risk, but are otherwise equal to other stocks, should be less valuable and therefore have higher returns. That is, you should receive a risk premium for owning such stocks. And this is borne out empirically by Bolton and Kaspersek. But investors who don't want to hold such assets are going to short them, and therefore these are the assets that you would expect to be beneficiaries of climate change. And so these are going to be in hedge portfolios. And so climate hedge portfolios that will short assets that are exposed to climate risk and go long assets which are expected to do well, relatively well in a climate change, will be in the situation where they're shorting the stocks that have a risk premium. and therefore this hedge portfolio is going to end up fundamentally with a negative risk premium. Now, that's the bad news about hedge portfolios. The good news about hedge portfolios is that if indeed climate turns out to be worse than the market expects, then there's going to be repricing of assets, and the hedge portfolio will increase in value. And if we think that the market does undervalue the risk of climate change, then this portfolio might be expected to have substantial increased returns in the future. But of course, if climate change turns out to be less bad than the market currently expects, this should underperform. So that's the theory of the hedge portfolio. How do you construct such hedge portfolios? Well, there are a lot of answers to this question, and it might be a long road before we actually get a good answer for it. It's basically, we need to try to figure out who are the winners and who are the losers from climate change. And that can either be approached with characteristics of firms, such as ESG characteristics or location or sector characteristics, or maybe balance sheet characteristics. And this effort to try to identify, based on insufficient data, which are the winners and which are the losers, is relatively complicated, but it's also the thing that Wall Street and the city and you know, all financial institutions are dealing with. How do you decide who the winners and losers are going to be on any kind of a risk, let alone climate risk? This is not a new problem. It's an old problem, and all this fuss about whether ESG is adequate or not, no data set is going to be adequate to actually answer this question. So I'm going to show you, we're going to use today two hedge portfolios that we follow a lot at the VRI. And one is based on fundamental information like sector, and that's what we call the stranded asset portfolio, and it's long the S&P 500, an ETF, short 70% of a coal ETF, and 30% of the broad energy ETF. So this is defined just based on the sectors. The second one we look at is what we call the climate efficient factor mimicking portfolio. And this is developed by Jean-Luc Denard, Brian Kelly, and myself. And this is a fund of funds. That is, we're going to look at a whole collection of publicly available funds which have some kind of climate credential. They're presumably some blend of ESG and hard thinking and some kind of analysis, and figuring out, each portfolio manager is figuring out what he's going to do. So we want to form a portfolio of these funds. It's a long-only portfolio, and it's going to change its weights over time. This portfolio, we're going to minimize the variance of the portfolio and maximize its correlation with climate news after taking out the effects of standard investment factors and taking out the effects of the stranded asset portfolio that I mentioned above. So this is like a second climate portfolio. It's in addition to the stranded asset portfolio. And we do this using, I think, a year of data, and then we hold the portfolio for a month and then recalculate it. Okay, so there are a lot of details in this. There are complications of forming big covariance matrices with short samples and shrinkage estimators and stuff like that. But anyway, this is now being done on VLab, and this is what the portfolio held throughout January. It had just two funds in it, these two funds, and they're almost equally weighted. In December, for the month of December, it was three funds, but the first two stayed there, and there was a third fund which was in it a little bit. And I think maybe tomorrow there's going to be an announcement of what the February fund is going to be. So when we look at returns, these are all going to be out of sample returns. And in fact, because the algorithm is built into VLab, it it's very out of sample. I mean, it's the way of doing it is not changing over time either. So in addition to these two assets, the stranded asset and the climate efficient factor mimicking portfolio, we look at three other benchmarks. One is the ACWI, another is the S&P itself, and the third is a sort of a naive portfolio of just not holding energy stocks. It's S&P minus the energy sector. And if you look over the long horizon, this is how long we have each one, they all, except for this naive one, have positive Sharpe ratios. And the stranded asset portfolio is really just as good as the Spider, even though it might have a negative risk premium, but it's repriced often enough that it has a positive return. And the climate efficient factor portfolio is slightly, has considerably higher returns and a little bit better Sharpe ratio. But if we look at these over 1 year or 5 years, at 1 year, you see the return for each of these is dramatically negative, with the naive one being the worst. Sorry. So you see, they have been doing very badly recently, although over the 5-year period, they all have positive returns. So one of the things we're going to come back to is what's going on now. And the title of the talk is, have capital markets forgotten about sustainability? Is a question about what's happened to these two funds here, the stranded asset and the climate efficient portfolio fund, for example. And here's a picture, and the green one is the stranded asset fund, and you can see it moves ahead of the two basic funds substantially, starting really in 2019. And then this is a big acceleration in 2020, kind of flat a little bit and starts downward, and it comes down a fair amount toward the end here. And this goes up through end of to yesterday, I guess. The CEP was really very similar to the S&P until 2020, and then it had a big acceleration, has been more or less flat, and now is declining as well at the end here. So it's these downward movements here that are the evidence that the market is not responding to the hedge portfolios the way it has in the past. And you see the naive portfolio does the worst. Okay, so now what are we going to do with these climate factors? Well, one thing we could do is invest in them directly to achieve this climate hedge performance. They're both investable portfolios. One needs to be changed every month. The other one is really just a fixed weight portfolio. Secondly, we might be interested in portfolios that have a high beta on these funds to achieve similar performance. And this is what you might think of as a way of detecting greenwashing. That is, do the other funds that your portfolio that you've put together, is that correlated with these funds? If you want it to be more correlated with them, you could add something in which has a high beta on these funds. So if a fund is simply advertising that it's green, but is not actually effectively performing, then it might be the fund is greenwashing. And then another thing that you might be interested in is doing a test of whether banks are green or brown. In other words, we could do stress tests of banks examining the impact of rising climate risk. The success of all of this has to be viewed, first of all, as stochastic, because all these things are stochastic. And second of all, of course, it depends dramatically on whether we have the right hedge or good hedge portfolios. And really, you can do this with a whole variety of hedge portfolios, which are formed different ways, as long as you think that all of them have some actual green credential to them. Okay, so how can we detect greenwashing? Well, I guess I just said this. I'm gonna look for positive betas on these climate hedge portfolios. Okay, so what do you see when you do that? Well, for example, here are the top 10 funds that we have measured by, I think their Sharpe ratio. And this is as of now. So this is a solar fund, which is the highest. Here's its return over I think the last 5 years, volatility, Sharpe ratio. These are correlations with climate news measures, 2 climate news measures. And this is the CAPM alpha, that is, you just regress it on the SPY. And then the next 2 columns are the columns that you might be interested in from a greenwashing point of view. This is the beta on the stranded asset portfolio, and this is the beta on the CEP portfolio. Actually, it looks like I've sorted this in this table. I've sorted it on this beta. So you can see which are the funds that have the highest correlation and highest betas on this climate efficient portfolio. You could, of course, sort it on any of these factors just by going to VLab and selecting which one you want to. So in this case, I like to think about these 2 columns as being different flavors of greenness that you might expect from a portfolio. That these would be more focused on sectors, you know, the energy sector and the coal in particular. And this is more associated with other factors that are important in climate change. So now let's talk a little bit about bank exposures. We think banks are exposed to climate risk because they hold assets which are exposed to climate risk. And so it's important to know whether they are overly exposed to these kinds of assets, so that a policy which leads to decarbonization would actually create a financial crisis. We don't want that to happen. And so regulators are trying to make sure that this question, that this does not arise, that there's a conflict between mitigation and financial stability. The banks, I think, know that this is happening. All central banks around the world are doing this. And so one of the things we see is that we see climate betas on the banks were rising for a while, but seem to be falling today. This could be a response to what they see as future regulatory pressure, or maybe it's simply that they don't want to hold these kinds of long-run risks. So in the paper by Ian Young, Dick Berner, and myself, we look at regression of bank returns on the market and one of these climate factors. In this case, we're using the stranded asset factor. And we're doing this with a dynamic conditional beta model so that the betas are time varying. And what we're interested in is this climate beta. because that tells us whether the climate factor is actually a significant determinant of stock returns. So it allows for both volatility and correlations to be changing, and it allows for the banks to change their portfolio mix in a way that is reflected in their in the climate beta. We calculate C risk, which is the capital that the bank would need to rebuild its capital base if we have a climate stress scenario, which is an extreme move in this climate factor. And it's calculated the same way we calculated S risk years ago. There's a prudential capital ratio that we want to get to, and it depends on the liabilities and assets of the bank. And then we want to know C risk is the expected value of the capital shortfall conditional on climate risk. Now, it turns out that banks might be undercapitalized even without climate risk, in which case we see that the capital shortfall is not really attributable to climate risk. It's attributable just to the bank's behavior and maybe other factors going on. So we've created a new measure now, which is called marginal C risk. That is, it's the difference between the C risk with climate change and the C risk without climate change. In other words, it's how much does the bank's balance sheet, the bank's market cap go down with after the stress, if we have a climate stress event. So C risk itself is a measure of capital adequacy, but marginal C risk is a measure of its exposure to climate risk. And from the point of view of this group, you know, the way we're talking about it, I don't know which one we're interested in, but they're different measures. So here's a picture of the climate betas over time of the 10 largest US banks. And what you see is this big rise in at the end of the sample period, which may be a rise due to perceptions of climate risk. It might be a rise in terms of the value of energy loans in the portfolio, or a variety of other things. If you look at the same thing for the UK, you see a similar picture here, although there are some other high points in the UK. We now do this on VLab, and so here is just an example. This is BNP Paribas. This is the climate beta, and you see again the same rise that I just showed you in this picture. It's a little noisier because the other picture was smoothed to get rid of some of the peaks. If you look at the marginal C risk, you'll see the picture has the same rise here, but it's this is C risk. That was the beta. This is the C risk, and you can see it's certainly tied to the climate beta. And then if you look at the marginal C risk, you see this picture. And interestingly, on the marginal C risk, we should point out where zero is. Zero is here, so that back over the past, you know, it's fluctuating around zero. So it isn't really clear that there's this big climate sensitivity of BNP Paribas. It is $20 billion, $30 billion and so forth during the pandemic and its recovery, but it's now down to a pretty small number again. If you look at the European banks as a whole, ranked by their total C risk, these are the top 10 banks in Europe. And if you look at the marginal C risk, you'll see for all of them, it's actually a good bit less than the total C risk, suggesting that the climate effect is only typically a small part of the their needs to get back to 8% capital ratios. And then if you aggregated this all over the whole world, you see a very substantial rise in sea risk. It's kind of flat over the end of this sample period, but it's rising. And you'll see it rise very substantially here. This is, a lot of it is due to the Chinese banks, which are quite undercapitalized. Okay, so now let me finally say a little bit about what we see today. For one thing, we see volatilities around the world have come down a lot since last year, but we still don't know about this energy stuff. So I'm reminded of a quote from Star Wars Emperor. If you remember the evil Emperor in Star Wars, one of the things he says is, everything is proceeding as I have foreseen. And the question is, did we foresee this? Or did he really foresee it? And the fact that sustainable funds are underperforming is really not surprising, because the energy sector has done extremely well this year, or last year, I guess I should say. But the question, and because it's either short or underweighting the energy sector, all these sustainable funds have done badly. But why has the energy sector done so well? Well, maybe it's because of the way the private sector approaches decarbonization. And if you think about the long run risk of stranded assets, the same as for this hotel owner, it would not be surprising for them to underinvest in exploration of new oil sources, of building new refineries. These have very long horizons, and it's not clear that the energy horizon is that long. So how do we get empirical evidence on this? I'm just going to give you a little bit. One thing is that stock prices, regardless of anything else I've said, should reflect present discounted values of future expected earnings. And so therefore, PE ratios are high when the future earnings are expected to be high, and they're low otherwise. In addition, stock prices reflect forward-looking expectations, but book values from the balance sheets only reflect current or past historical values. So if this is really true, we would expect to see PE ratios to be low for the energy sector, and price to book ratios to be low for the energy sector. And if we look at data from 20 to 21, you see across sectors, PE ratios are the lowest for the energy companies. In fact, they're even lower in what's this, 21, I guess, than they are in 20, they're negative. And if you look at price to book ratios, again, energy is the lowest. There's a lot of evidence that the capital expenditures are low, and I think it's quite likely that this is a story which is at least part of what's going on. But there are other impacts that are really important for us to mention. One is we see inflation higher than we have in many countries, and energy prices are a big part of this. Another cause is the supply chain collapse, which in fact is also partly due to high cost of transportation, but also partly due to pandemics and deterioration of the relationships with China. So, and then what are we doing about it? Well, we're raising interest rates to slow the economy. So that is another step along the same direction. But in addition, I haven't mentioned the geopolitical stuff, but clearly high energy prices have something to do with the Russian invasion of Ukraine. And this is a major reduction of supply. And in Europe, you know more about this even than we do. And I think the implication is that even Putin himself must be a climate activist. He has reduced the supply and is trying to diversify his economy with a catastrophic war. He knows his resources will be worth less in 10 years and the demand curve will be more elastic because of European renewable energy. So he is acting just like this hotel owner. He's restricting supply and trying to take this excess reserve and run a war with it to diversify his economy. At least this is a possible explanation of what we're seeing. So does it turn out the same way? Well, it turns out that the fossil energy is now, he's selling at a higher price than he did before, and the ruble has more than recovered from the initial invasion. So I think it's not unreasonable to think that this same long-run risk story has a lot of explanations. You can see some of this in China too, but I'm not going to talk about that. So should we be pessimistic about the climate from what we're seeing in these asset prices? Well, I don't know. It's always been clear that decarbonization would require consumers and businesses to shift from high-emitting products to low-emitting products. And high fossil energy prices would always be part of this process. So, in fact, the high energy prices that we're seeing are really part of climate accommodation. And if consumers add insulation so they don't need so much heat, they buy electric cars, reduce driving, all this stuff is part of the mitigation process. So conveniently, we can blame Putin for inflation rather than the radical climate activists or climate policy. It's insofar as fossil energy supply is increased, this may delay decarbonization, but I think there's a lot of evidence that some of the big expenditures that we're doing right now to try to increase supply are actually going toward renewables, or at least into the natural liquid natural gas transportation algorithms. So in any case, I don't think that what we're seeing here is necessarily bad news for climate. We may see that this is a really strong push toward investing in renewables, which in fact is going to increase energy security and independence for many countries. So what would be different if we had actually put in a carbon tax? And this really refers more to the US, but to some extent to Europe as well. Well, instead of the fossil energy companies getting all these excess profits from the high prices of oil, the government would get this. The profits would be siphoned off by the tax on emissions, and portfolios such as the stranded asset portfolio would be performing well because the stock prices of these companies would not go up so much if they had to pay higher taxes for their emissions. Inflation would be lower if the revenue were directed either at subsidized renewable energy or possibly reducing deficits. And so should we abandon our investment in hedge portfolios? Well, in a net zero world, ultimately fossil energy stocks do go to zero. So hedge portfolios are likely to outperform if decarbonization continues. And so I think, there has been a bad period of investing in sustainable stocks, but not necessarily a bad investment today. And I think with the accelerated decarbonization due to the Russian invasion, I think the Biden climate bill is a big step forward in a very slow-moving US climate response, and the EU Green Deal is a step in that direction. And so I think actually this whole experience might move us in a climate-friendly direction. So when I explain this to my three of my grandsons who are sort of pessimistic about the future, it makes them happy. Okay, thank you. How do I get this big again?
Somewhere there'll be a stop screen share button.
Oh, that's what I need, stop share. There we go. Okay, thank you.
Oh, for some reason, Claudio's lost
Yeah, Claudio disappeared.
connection.
What happened?
Claudio
Claudio's lost
disappeared.
his-
Claudia's disappeared.
Yeah.
Did I get?
No, it's not because of you. No, no, you didn't.
Didn't do that. Okay.
No, you didn't give him.
We
No.
did it last week in the talks we were having in unpredictability. So yeah.
Maybe we ran out of time. No, well, not quite yet.
No, not quite.
No.
So Rob, I mean, one comment, how you mentioned at the end this climate bill of Biden, the IRA, the Inflation Reduction Act,
Right.
that yesterday Europe tried to, here is a good, I mean, here in Europe, I mean, we are discussing how to counteract that because
Right.
is this showing up in your results, or because of what you said that is going so slow, it will not, I mean, it will take time until you see the effect of these interventions?
Well, I think, I mean, it turns out if you look at I showed you some of those pictures were December. If you look at January, they look better. So already we're seeing a turnaround in sustainable investments. At some extent, turnaround in the market as a whole, but I think that the sustainable, these purely sustainability stocks like, you know, wind and solar and so forth have had a good run in January. The Biden bill absolutely refuses to put any restrictions on fossil energy, but it's subsidizing all sorts of renewable stuff, and including a lot of research in renewables, which, you know, I think really is an attractive way of doing policy. It's protectionist too, which is of course what you're referring to, because it says, you know, okay, but we're only going to subsidize the stuff that's made in America. And at least one answer to that is that, well, we'd like to see you do the same thing, and then we're on a level playing field again, and it's a level playing field where we're all making big contributions to the climate problem.
Mm-hmm.
Now, you know, I don't know whether I mean, probably China can do that with a stroke of the pen. They don't need congressional approval or any of these complicated things that we have to deal with. But and I think there is a possibility that China would do that as well. I think climate is one of the things that they are more willing to collaborate with us on than most of the other stuff that's going on. So I'm kind of optimistic that we may have come to a better place in this climate discussion than we were before.
Agreed. Yeah.
Mm-hmm.
And it's just, you know, when you see these funds underperforming, you say, wait a minute, it's all in the tank. But I don't think that's right.
No. And part of it's also the huge increase in the costs of making renewable equipment. I mean, wind turbines are very much more expensive. solar cells have got a bit more expensive, partly because of China's lockdowns, and some of that will unravel very soon.
I hope so. I mean, as I have said, we have excess demand for our goods. China has deficient demand for their goods. There's a lot of scope for getting together.
Yeah.
Is Pareto superior?
It's I don't know whether it's really going to happen, but I'm hopeful that we can find some common ground.
So you were mentioning that we probably have seen an acceleration in the transition, and transition can be ordered or disordered. And it seems that this acceleration has kind of led a disorder in the transition. We expect, in a way, this say the global system to become resilient and a more ordered transition to set in.
Well, I think all these investments and public policies that are being proposed and implemented are thinking about resilience. I think, you know, there are the steady flow of Russian gas that people were counting on in the past really is not so steady. It doesn't look so good, and the supply chain effects that we're attributing some of this inflation to are again outside of our control in many respects. And I think, you know, I think it leads to a sort of a protectionist point of view, which is maybe the flip side of resilience. But I do think we're moving in a little bit in that direction too. We're seeing that. I'm not sure I'm in favor of that part of it, but anyway.